Welcome, lecture 43. We have seen an introduction to CDMA, a very interesting topic, very lot of insights into what used to be advantages for military communications and how it has played a very important role in cellular systems. So basically what we were saying was CDMA has formed the backbone of what we refer to as the third generation cellular systems. And third generation cellular systems is not, as we saw in the introduction, is not a single standard, but it has evolved over a period of time. So there are variants that are called 3.5G also, so that has also been based on CDMA. And there are two dominant flavors. One is what we refer to as CDMA 2000. It was introduced into the market as a competitor to GSM. And GSM itself evolved to a system called wideband CDMA. So if you go by history, they should have been competitors, and they were. But eventually, in the fourth generation, they became a single system called LTE. But in the third generation, they were both CDMA-based systems. Both had some unique characteristics. We will study that. And you'll also see that the design of a cellular system based on CDMA is something that is far from non-trivial. Far from trivial. It's highly non-trivial because the complexities of how to design, basically you have taken something that had a very different application in military communications and you're using it for a cellular system. And we'd like to see what are some of those benefits. So, but for now, the first thing that wanted to just refresh your memory is the understanding of what is the basic pulse shape. It's a rectangular pulse shape, and what we will actually be using is a shifted rectangular pulse shape with a scaling to make it unit energy. And we showed that the corresponding spectrum looks like this. Now, there is a difference between the terminologies that we will use, and we will maybe just a good point to highlight that is the difference between symbols and chips. So, never have a confusion between symbols and chips. Whenever we refer to chips, that means we are referring to the signal which has already been spread. Symbols, there are symbols which are being transmitted in the in the spread spectrum system, but it could also be before or after despreading. So therefore, we have to interpret them carefully. So in general, the convention is symbols means it is the narrowband system. Chips means that it has been spread, so the information is still there, but the fundamental waveforms are different. Okay, and we had looked at the spectrum, how the once you spread it, the bandwidth of the signal expands by a factor of q. So we pick it up from there and build up our development of today's lecture. Okay, so the pulse shape or the waveform that we are using for direct sequence spread spectrum, we have not yet introduced it as a CDMA system, still at the basic level. We say that the pulse shape or the shape that will be used for representing a symbol is not a single pulse, but it's a combination of q pulses. So I is equal to 1 through uppercase Q, C subscript of Q, GC minus QTC, where the GC has this waveform 1 over root T, not TC. This is TC, and this is the basic pulse shape, and these CQs are belonging to plus minus 1. So basically it's a sequence of plus minus 1s which are then modulated. Now I hope you are comfortable with this notation, GC T minus QTC. That means for if the first first chip was a plus 1, second chip minus 1, third chip minus 1 plus 1, the waveform that we are talking about is up to TC is plus 1, minus TC is minus 1, plus 1. Okay, this would be the waveform corresponding to that, and that's what is represented. And this is so one symbol is what we are trying to represent of the narrowband system. This corresponds to Q chips, and always make sure that you're comfortable with that. And so typically, if we keep it very simple, if the symbols, let's say, can be either a +1 or a -1. So this represents a +1, a -1, the symbol. The corresponding chip waveform, let us say, is 1 0 1 0 1 1. Again, this may be material that you are very familiar with, but I just want to avoid any confusion. So 1 0 1 1 or 1 -1, maybe 1 -1 1 1. So if I want to send the waveform of the other polarity, basically it will be a flipped version. So again, the basic operation of spreading, I'm assuming you're familiar with. Now, very often in the context of the spread spectrum systems, again, I just want to say that at the beginning itself, we are talking about a waveform that is binary. For example, Walsh-Hadamard code, the spreading code. We'll talk about it in terms of ones and zeros. But when it actually gets transmitted, it is not 0, but it actually is a +1, -1. So there is a mapping that will map it to 0 to -1 and a +1. So that mapping is 2bi -1. There's another mapping which is 1 - 2bi, and that will map a 0 to a +1 and a -1. And again, it does not make a difference, but just be aware that we will always, when it actually comes to the waveform implementation on the channel, it will be a +1 and -1. But very often you'll find that discussions regarding the spreading codes will be in the context of zeros and ones. So again, always make sure that you have to quickly translate it into a waveform that okay. So with this basic introduction, now to move it from just a single user system into a multi-user system, and how to build on this particular effort. But before that, let's answer, or let's get a feel for the communication system as a whole. Okay, so I would like to look at a direct sequence spread spectrum system and what sort of receiver we would have to use for that. And this is a good starting point for us to get a feel for the spread spectrum systems, and then how do we expand them into a multi-user system. So typically the received signal R of t is the transmitted signal plus some impairment. Okay, and the u of t, the transmitted signal, is b, some value ±1 square root of EB, that is the energy of the bit, g of t, that's the waveform that we have used for the symbol. Again, at this point, we are talking about spread spectrum systems, so g of t is the spread waveform, plus z of t. Okay, and assume that z of t is AWGN. The optimum filter in AWGN is a match filter. So basically, you must apply a filter that is time reversed and conjugated, and then sampled at the end of one symbol duration. Okay. Now, a match filter can also be implemented as a correlation based receiver. So it's very intuitive and helpful for us to look at it in the form of a correlation based receiver. So my optimum receiver will be a match filter implemented using a correlator. So my decision statistic will be of the following form. Again, this is a material I'm assuming is very familiar, but good for us to have the foundation. So the decision statistic will be, you multiply the received signal with a conjugated version of the pulse shape g of t, okay, integrated over 0 to t, a symbol duration. Okay. So, now go back and substitute, this will come out to be b times root EB integral 0 to t g of t magnitude squared dt, okay, plus integral of 0 to t z of t g star of t dt. Okay. Now, we will call this as a noise term eta, okay, and basically we have made the assumption that this is a AWGN 0 mean, okay, some impairment that has happened. Okay. Now, is this, if I say that this is equal to 1, would you agree? It is 1 over root t, but there are q of them. When I add all of them, basically I will get each of them contributes Tc, right? Each of these pulses will contribute Tc. There are q of them, so it will become qTc divided by t, which is equal to 1. Okay, that's the relationship. So this is equal to 1. So what we get at the output is b times root EB plus eta. Okay, expected value of eta is 0. Basically, it's a 0 mean Gaussian signal that has been filtered. So therefore, it does not affect the mean. We're interested to know what is sigma n squared. Okay, so that will be expected value of magnitude of that of eta squared, 0 to t z of t g star of t dt magnitude squared. Okay, that's the variance. Okay, so I just need to want you to be comfortable with this step, because we will see many times this operation, and again this is something not new to you, but just wanted to make sure that we are comfortable with this. So I'm going to write this magnitude squared as two integrals, one the integral and then its conjugate. So this is expected value of integral 0 to t z of t g star of t dt, then integral 0 to t, I will change the variable of integration, I have to conjugate everything, z star of tau g of tau d tau. Okay. Now group the terms, take the expectation inside. This is z of t is white noise, so expected value of z of t z star of tau is equal to correlation. So if it is not aligned, it will give 0, so it's a delta function n naught t minus tau. So only when both are aligned you get the power of the noise, otherwise the expected value goes to 0. Okay. So and of course once this constant comes out, t and tau become the same, you get integral 0 to t mod g of t whole squared, that will be give you equal to 1. So sigma n squared equal to n naught. Please verify that. Okay. So the last step, again very important for you to note, SNR of my decision statistic. Right, that's the what's going to determine whether I will make a correct decision or not, will be equal to b times EB, that's the signal power, by the noise component EB by n naught, sorry b squared it will come, right, b squared, yeah, and b is plus or minus 1, so this comes out to be EB by n naught. Okay. Now at this point you wonder, you went through all this process to tell me that you still have EB by n naught, you have not done anything to improve the signal to noise ratio. The answer is yes, not done anything to improve the signal to noise ratio. And that is one of the fundamental things that you need to learn, that if your impairment is only white noise, spreading does not help at all. Spreading does not help at all. You just expand the bandwidth, you contract the bandwidth. In both operations, the noise does not play a role, and therefore you end up having the original noise spectral density as before. So there is no advantage for spread spectrum in pure AWGN. Okay, but multipath, oh, huge advantage. Interference, huge advantage. So in a cellular system, it's both multipath and interference. So therefore, the advantages are coming. So maybe just a footnote saying that, okay, in AWGN, it's not going to give me an advantage at all. Okay. That's an important, so now given that you already know or are starting to think about the receivers, maybe the next step would be to write down some possible receiver structures, for spread spectrum receivers. Okay, you may say, well, I already designed the correlation based receiver. I just want to take you one step beyond that initial perspective to the way we would actually like to implement it. Possible structures for direct sequence spread spectrum systems. Okay. Now, of course, we said that the match filter approach is the way we are going to do it. So take the received signal, multiply it with G star of T. This is basically one symbol long. After that, it will be followed by an integrator from 0 to T, again one symbol duration. Whatever is the output of this multiplication process, you integrate it over one symbol period, and then once a symbol duration that is at symbol rate, you sample, and that will be your decision statistic Y. Okay, this is the structure that we have just now implemented. So this is the match filter based approach. So this G star of T, this match filter approach is for anything, whether it's spread spectrum or not. So this waveform, when it's a spread spectrum system, includes the effect of spreading, which means it has Q chips, and then includes the effect of spreading and the chip waveform, effect of spreading and the pulse shape of each chip. Okay, pulse shaping of each chip. Okay, it includes both of those. Now there is another structure, very intuitive, which more or less emerges from here, but it helps you to start to think in the way that we want to approach these spread spectrum systems. Is now when we start to have multiple users, one of the things that we will have to allocate to them is different users will get different spreading waveforms. That's how we are going to preserve orthogonality. So which means that every time something changes, your match filter has to change. So now if you say that I don't want to keep modifying my match filter, I want to have a structure that is a little bit not so much dependent on the current spreading sequence, there is a second structure which is very interesting and helpful. So R of T multiplied by GC star of T. Okay, now regardless of what your spreading sequence is, GC does not change. It's still that rectangular waveform for one chip. Okay, and this one also, it's a match filter. So we will now integrate from 0 to TC integral dt. Okay, 0 to TC, and the output I'm going to sample at chip rate. Okay. So basically there is a chip rate clock, just like in the previous case you would have a symbol rate clock, chip rate clock which is controlling this sampling device. But we are not done yet. We still need to despread. What we have done is you have achieved the best detection possible for each chip, but now you need to remove the spreading. So whatever was your spreading sequence, assuming it was some sequence of plus minus ones, if you multiply it again by the same spreading sequence, what happens? You will remove the spreading. So basically the spreading sequence, same spreading sequence, if you multiply, then what you get is a sequence of chips which we can then use to do the subsequent detection mechanisms. So basically there are two ways of looking at the direct sequence spread spectrum system, either at a symbol level. It's good as a starting point to do that, but very quickly move into start thinking in terms of chips and how we work with the chips, and that is very helpful for us. Okay, so now would like to move into leading us into the multi-user environment. Okay, so we talk about a spreading sequence. We will use the notation C subscript Q. Q stands for the chip index. So this, we will call this as a spreading sequence. Oh, am I spelling spreading sequence? It is also called a signature sequence. It's also called a signature sequence. So basically something that uniquely identifies a user. So moving into the multi-user environment, maybe the signature sequence is a very appropriate term. So, and this is unique for every user. Unique, that's the only way we need to be, we can separate them. Unique for every user. Okay, that is an important element. So let us look at user K. Let us look at two users, K and J, and start to make some observations about their spreading sequences. User K, the waveform for one symbol will be a combination of the waveforms of the different chips. The chip waveform is the same, but the chip values are different. So that is captured in the following form. Q is equal to, you can do it 0 through Q minus 1 or 1 to Q. I apologize if I have mixed up, but it is basically a total of Q chips. Ck subscript Q Gc of T minus QTC. In order to write this one, you must have starting from Q, because the first chip waveform should be at the origin. So it should start from Q equal to 0. For the user, next user, let's call the user as user J. User J, you must have a different waveform, and we will now quickly, and so the duration of this is T greater than or equal to 0, less than or equal to T. That is the symbol period. So the waveform, that the spreading waveform lasts a duration of one symbol of the narrowband system. Symbol duration. It's made up of Q chips, and each of the chips have got its own unique, the same waveform. User J, G subscript J of T to denote the symbol waveform of user J. We want it to be different, unique. So Q is equal to 0 to Q minus 1. C subscript J of Q Gc T minus QTC. Notice the Gc is the same. So regardless of which spreading sequence you are given, the match filter will remain the same. The processing after the match filter is what will change. Okay. So the two components here are, this is the signature sequence, that's the signature sequence component, and this is the pulse shape component, chip level pulse shape. Okay, the combination of the two give you the symbol waveform, and then that's okay. Now we already wrote down this property, but after we wrote down in the form of chips, will this property hold? Properties, okay, integral 0 to T mod Gi of T whole squared dt is equal to 1. Is that correct? Would you agree? Yes, because what is this? It's all these type of waveforms, right? If I take the magnitude squared and add, it will come out to be the right value. So yeah, this is correct. So this is one of the basic properties. The unit energy property is preserved. Okay, even after we do these. So this is true for all of the spreading sequences as long as your sequences are plus minus ones. Okay. Now what we would like to add in addition to this are the following. And now here it's where it becomes very interesting, and request you to pay attention, and if there are any doubts we will discuss that. So I'm going to first write down an orthogonality property. that both these waveforms must be orthogonal. Only then we will be able to separate them. Orthogonality property. The orthogonality property basically says that if I take rjk of tau, that means the spreading waveforms of the pulse shapes of the jth user and the kth user, define this as the integral. Basically these waveforms are defined over a period of time, but because I am shifting them, the most general form is minus infinity to infinity gj of t gk star of t minus tau dt. So in other words, basically I am correlating the waveform of user j with user k. Tau can be 0, tau can have shifts as well. What we would like to have is that this property is approximately or as close to 0 whenever j is not equal to k for all values of tau. So this is a very important property. This is the property of mutual orthogonality, right? So basically it's orthogonality, but it's between users, mutual orthogonality. Okay. Now there is another component that is that's very important for us. That is the next property, which is self-orthogonality. Self-orthogonality is also a part that is very important. Basically says that if I take autocorrelation of a user's waveform with itself at a delay of tau, this must be as close to a delta function. Okay. If I gave you these two conditions and say give me some candidate schemes for the spreading waveforms, what are some suggestions you could give me? What are things that will if you take white noise and take one segment for user k, self orthogonality is guaranteed, because white noise, if you only at 0 lag you will get any correlation, and take a completely different segment for another user. And now these two are independent segments of white noise, so correlation between the two does not exist, and therefore, so start to think in terms of trying to make each user's waveform look white. Okay, basically that's ultimately what we are trying to do, so that it is not correlated with other sequences, and it has only the correlation at 0 lag. At all other lags it does not have correlation. This is a very useful property. So 1 and 2, 1 being mutual orthogonality, self orthogonality being number 2. So conditions or properties 1 and 2 are pretty much the heart of CDMA, the heart of CDMA systems. The minute we get these two pictures in mind, because we will have, and let me substantiate that statement with the following. Okay, so I'm going to have an example with 3 parts. So example 1A. So if I now have a signal R of t, which is B1 root EB times G1 of t. That's user 1's waveform. But what's happening is there's a second user also in the using the channel. So in CDMA systems, both are using the same frequency at the same time, so they will interfere with each other. So the interfering signal is B2 root EB G2 of t, and of course as always there is noise present in the system, Z of t. Okay. So this is the case where what you would call as 2 users who are synchronous, because both of them are perfectly aligned in terms of their symbol boundaries. 2 synchronous users. Okay, synchronous users. Now very important that it could be any number. We have just taken a simple case of more than 1, and now please pay very close attention to. So what is the optimum receiver for user 1? Receiver for user 1 we say that okay, match filter is that's all I know. Maybe that's is that the right thing to do in the context of the of this environment? Let's take a look and see. So the decision statistic, if I do 0 to t r of t g1 star of t dt. Okay, if I do that and if I have satisfied the properties of mutual orthogonality and self orthogonality, in this case mutual orthogonality, what will happen? The second term when I do the integration goes to 0, right, because this will be equal to b1 root eb integral 0 to t mod g1 of t magnitude square dt. Now that is equal to 1. Okay, so we have gotten the desired signal. The second one is b2 root eb integral 0 to t g1 of t g2 of t g1 star of t dt. Mutual orthogonality says this term will go to 0 if mutual orthogonality due to mutual orthogonality. Okay, and of course the noise is a filtered form of the noise, basically let me call that as eta. Okay, so that is my decision statistic. So this is nothing but b1 times root eb plus eta. So what did it do? It took you from a multi-user environment to a single user AWGen like environment. Okay, all because you could satisfy mutual orthogonality. Now you could obviously this is applicable for n greater than equal to 2 also. So you can have, but the key thing is you must have waveforms that are orthogonal and the users have to be synchronous, so therefore it's an important element. Okay, second, now what if the users are asynchronous? So example 1b, asynchronous users you will capture in the following form: b1 root eb g1 of t. Please tell me how to write the asynchronous user. b2 root eb g2 with some shift t minus tau, call that, okay, plus z of t. Okay, apply the same decision the receiver mechanism. User the data of user 1 comes out. The second term, when I do the integral 0 to t b2 root eb g2 t minus tau g1 star of t dt. Okay. Now of course b2 root eb you can take out. The mutual orthogonality is valid for all tau. So therefore this term also goes to 0 or very close to 0, and therefore you are once again, so whether it is synchronous users or asynchronous users, you find that you are able to, because of the assumptions of, now how difficult is it to get mutual and orthogonality? That's the challenge, but if you have that, then you have the very powerful system. Okay, the last of the last part of the example, example 1c. Now look at this example and describe this signal for me. R of t is alpha b root b1 root eb g1 of t plus beta times b1 root eb g1 of t minus tau plus z of t. What type of channel is this? Multipath channel, okay, and it's got different multipath gains alpha and beta. So now what I do, I apply the same type of receiver, and what comes out is this one comes out as y1, and I get alpha times b1 root eb plus eta 1. What happened to the second term? Because of self orthogonality, right? When you are not aligned perfectly at tau equal to 0, that term goes to 0. Now, but the good thing is, if you now shift your correlation to align with the second term, you get a second output which will knock off the first term, but will preserve the second term. Beta times b1 root eb plus eta 2. So this comes out when you do integral 0 to t r of t g star of t minus tau dt. Okay, so basically if you slide your correlation instead of just aligning it, first time y1 you got with tau equal to 0, right, with this shift of the correlating waveform. This one at a value of tau. Okay, so basically you got these two. So you got now two copies of the data that you are trying to detect. Of course, this looks like diversity. And what should you do? Maximal ratio combining, or something that's as close to as best as you can. So basically you would do some form of diversity combining to get the best performance. And of course this was going to give you a benefit in the fading waveform, because alpha and beta could be independently fading. So therefore you will get the diversity benefit, and so you would try to do something like MRC if you can. And CDMA systems actually use a technique called the rake receiver, which is a form of diversity combining, as we have already mentioned. So the two properties are going to play a very key role. Mutual orthogonality is a key element or key feature that will help us deal with multiple access interference. Okay, it rejects all other user signals. This one rejects or suppresses multiple access interference, that is the interference caused by other users who are using the channel at the same time, multiple access interference. Okay, the other component is the self-orthogonality, and that is the one that helps us capture the multipath. This is the one that helps capture the multipath. And these are the two impairments in a cellular system, and these are the spreading waveform, and the receiver for the corresponding spreading waveform is going to play a huge role in helping us work with these. Okay, any doubts or questions? Okay, now we move into an interesting discussion. And hopefully this will start to build the intuition regarding the sequences themselves. So the question that we now ask is, okay, now where do we find such sequences? You know, this is all nice to write down mutual orthogonality, self-orthogonality, but I need to find these sequences. So again, going back to our understanding that we need to be looking at the random sequences or random types of sequences. So we will study basic properties of random sequences, and the best that we can do in practice are pseudo-random sequences. So we will basically, but first let us look at random sequences. So random sequences are defined as a sequence of plus minus ones. A random sequence of plus minus ones of length q, okay, of length q. Basically you can think of it as a segment of length q of a much larger sequence, if that will help, because you know random sequences are not necessarily defined for a specific length. Okay, now these sequences have the following properties, that if I look at two different indices m and n, they are not the same, then x of m and x of n are independent, and that is the basic property of a random sequence. They are independent. Okay? And because these are bipolar, plus minus ones, the expected value is 0. Expected value of m is 0. Okay? And now if I have another sequence y of m, okay, so now I can think of it as now the waveforms that I need for two users. And now we want to look at the properties of this type of a system. So first thing that I would like to do is autocorrelation. Autocorrelation property and how it manifests itself, and cross correlation property and how that would manifest itself. So Rxx of k, this would be expected value of 1 by q, because I am doing a summation over q, summation q equal to 0 through q minus 1 x of q minus k, okay, x of q minus k. Okay. So, as long as k is non-zero, this term is going to go to 0 because of the independence property if k is not equal to 0. And if k is equal to 0, then what we get is Rxx of 0 will be equal to 1, Okay. So, basically we can write Rxx of k to be equal to delta of k. Okay, that's a good property of the random sequences. Now move over and start to think in terms of multiple users. I need to worry about what will be the cross correlation between these waveforms. This would be expected value of 1 by q summation q equal to 0 through q minus 1 x of q y of q minus k. Notice I have dropped the conjugate because I am basically dealing with real sequences. Now this is a very important quantity for the following reason. When we try to look at the receiver for user 1 and I apply the correlation based technique, what is going to happen is the second term will contribute something. So basically there is a user 1 signal, user 2 signal, and then there is noise. So this user 2 signal is going to contribute a term that is going to be affected by the cross correlation. So ideally you would like this to be 0, but if it is not 0, what is the value? So that is what we are trying to understand. Okay. So what we would like to do is look at the mean and the variance. Mean you can easily show is equal to 0, but now I want to look at expected value of the magnitude square of this, because that is going to tell me how much is the interference power, because this is the correlation value, this is what is going to leak into my decision statistic. The magnitude square is going to be my interference power. So I want to look at 1 by q summation q equal to 0 to q minus 1 x of q y of q whole square. Okay. So basically I have taken q equal to k equal to 0, but again this is a useful form to say that okay, this is the type of interference power. So this is going to be the power of the interference. It represents the interference power of the interference component in my decision statistic. Okay, power of the interference. And so when I write down this form, I will again go back to the form that we had written down earlier. It becomes 1 by q squared summation q equal to 0 to q minus 1 x of q y of q summation m equal to 0 through q minus 1 different index x of m y of m. Basically if q and m are not the same, this expression will go to 0, and if they are the same, what you will get is basically you will get expected value of 1 by q squared summation q equal to 0 through q minus 1 x squared of q y squared of q. Okay, x squared of q will become plus 1, y squared of q becomes plus 1. So this value becomes 1 by q. Okay. What is the takeaway from this discussion? They said, okay, you took these random sequences and looked at so when I apply the receiver for user 1, some signal is going to leak in from user 2. The power of the interference that is caused by this leakage has got a 1 over q factor if I use random sequences. Okay? Q is my spreading factor. So the larger my spreading factor, the multi-user interference is going to go down. And that's the fundamental property that we have taken from spread spectrum systems. Because if you remember, I told you a jammer, a tone jammer, if I have sufficiently large spreading factor, what will happen? It will suppress the interference by a factor of q, and which means that if I have a sufficiently large spreading system, a spreading factor, it will pretty much suppress the interference. And you can see that this suppression is a very powerful one, and this is what we refer to as processing gain. Processing gain is what you get because of your spreading factor, and this is the reason why we do spread spectrum, not for AWGN, because in AWGN we will not get any benefit. So what have we covered so far? What we said was I would like to have multi-user scenario. The best scenario is if I can my multi-user waveforms will satisfy mutual orthogonality and self-orthogonality. Again, I don't know how to find such sequences. So, in the quest for the sequences, we come upon random sequences look like what we want. If you take Q long enough, autocorrelation, the self-orthogonality is guaranteed. Mutual orthogonality is not 0, but it's 1 by Q, which is quite good. We will get the advantage of the spreading factor. Okay. So this is the point at which we then say, okay, now where do you find random sequences? And we said, well, the random sequences don't exist, so therefore we have to go with PN sequences, pseudo noise sequences or pseudo random sequences. So pseudo noise sequences. Okay. Can I assume everybody knows about PN sequences? Is that something I can assume, or do we need to spend a few minutes just to clarify the concepts? PN sequences, studied it in digital communications? Yes? Okay. Okay, I'm not getting an affirmation. So maybe we should spend a few minutes. Okay. There is a class of PN sequences which are called M sequences, which are very, very widely used in CDMA systems, and these are also called maximal length shift register sequences. Shift register sequences, I would definitely like my students to be familiar with M sequences and their properties, because these are so widely used. Okay, they are also referred to as linear shift register sequences. So again, we will the name becomes very clear when we look at the properties. So what you do is you look for primitive polynomials in GF2, polynomials. Okay, once you have the in GF2, and once you have these primitive polynomials, and I'm sure you would have, so basically, for example, this is a primitive polynomial. 1 plus x3 plus x4 is a primitive polynomial in GF2. Now, such primitive polynomials we will take and construct it into a interconnection of shift registers. Okay, basically, the way we would do this is we would write this in terms of delays. So this would become 1 plus d cubed plus d4, and the linear shift register sequences, feed forward shift register sequences will be a delay. 4 delays is what I will need, always moving to the right, d and d. Okay. So the output of the third delay is the coefficient of d cubed, and the output of the fourth delay is the coefficient of d power 4. So basically I have to add these two components. So that will be 1 plus d cube plus d4. That's basically this is d cube plus d4. Now because of the binary property, which says that if I add that to itself, that's what it means. So you can write it as take 1 to the other side. So 1 is equal to, the input is equal to d cube plus d4. So basically the shift register sequence, oh, what did I do? Okay. So, this is the implementation of this 1 plus d cube plus d4 in a binary context. So, basically now think in terms of zeros and ones, not as plus ones and minus ones. Once we finish generating it, then you can go back and think about okay. So, basically let's call these variables in the following form. Let's call this variable as x1, x2, x3, x4 and I. Okay. So, basically if I initialize x1, x2, x3, x4 with 1, 0, 0, 0. Okay. That is my starting state. You can start with except the non-zero or all zero state, you can start with any of the other states. Basically you initialize x1, x2, x3, x4. The operation says I do exclusive OR of x3 and x4, and that has to go back as my input, and that I will call that as I, okay, and that is 0. Okay. So, at the first time instant I have initialized x1, x2, x3, x4, that will decide what the input I is. Okay. So, now we have all these. At the next clock cycle, what happens? All these guys will move to the right. Okay, every one of these will move to the right. So, 0 moves to this position, 1 moves to this position, I have 0 and 0. So, 0, 0, the exclusive OR comes here. So, basically now you start to see the sequence. What is my output? This sequence. So, the first time instant this was 0, next time instant it was 0, and then you can fill up. Okay. So, just so that we won't spend too much time on this, please when you get a chance go through and write down this sequence, and what you will find is the following. The sequence that you will get at the output will be of the form 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. Okay. And then you will find that the sequence repeats itself. Then you will get 0, 0, 0, 1, 0, 0, dot, dot, dot. Okay. So, basically this is one full copy of the waveform of the sequence, and then this is a repeat. Okay. You can verify that this has a length 15. So, this is nothing but 2 to the 4 minus 1 equal to 15, and this is the basic property of maximal length shift registers. So, if you get a sequence that repeats only after 2 to the power of m minus 1, then you get a maximal length shift register sequence. It is called a PN sequence for a very specific property of the randomness of the form. It is deterministic in, because if you initialize it correctly and you know what the feedback taps are or the interconnection taps are, you can actually predict the sequence. So, it is not random in that sense, but the occurrence of the zeros and ones because of the GF2 properties, the primitive polynomial, all of that, you will find that it has a certain pattern that is very helpful. Okay. So, let us stop, we will continue on this. Okay. Thank you.